I'm Mirza Rahman, and I will present our org, CellularLint, which is a systematic framework for identifying inconsistent behaviors in cellular network specifications. So before we go into the details of our framework and the methodologies, I would first like to talk about the cellular networks in general. So as we know, cellular networks such as 4G or 5G is very widely used in our day-to-day life, which is we use them for our mobile devices, vehicular networks, and IoT networks, and so on. And these networks are actually governed by a set of specifications which go through a set of versions and different releases and written manually. And if this specification has any kind of errors or confusions, that can lead to different exploits in the mobile devices, and these exploits can later fall under the adversarial attacks. And so our question here is are these specifications consistent or inconsistent? So let's look at an example. So these are two text sequences taken from the NAS or 4G NAS specification, where we can see for the attach reject messages for the same cause 14, it is suggested to move to two different substates. And now if a developer is supposed to design the 4G implementation based on this, he or she might be very confused. And finding such inconsistencies manually could be very laborsome, and because there are like lots of specifications with thousands of papers of documents. So our question here is it possible to devise an automatic framework that can, a framework that can identify inconsistencies, and later we can map them to the device implementations or differential design choices. So let's look at our approach. So our approach is mostly motivated by natural language processing. So we use the language models here. So that's why we first take the specification documents from the 3GPP archive, and we build our corpus on that. And there is a parallel processing here. We also take the context preserving sequences. Please take a look at our paper to know more about the context preserving sequences. So we approach to our first challenge. The LLMs we take are not domain specific, right? So we have to make them understand our cellular network specifications. So that's why we pre-train them on the network specifications, and in parallelly, we also calculate the embedding vectors from the context preserving sequences. So please note that these embedding vectors are not used for training. They are only used for filtering. And now is the next challenge. So we do not know where to look for the inconsistent pair of sequences, right? Because there are thousands of documents. And we also don't know how to formulate the problem for the LLMs. So that's why we first do an uninformed fine-tuning, which is a general NLP task. We'll talk about that later. And also for the filtering task, we use the similarity check on the embedding matrices, embedding vectors. So for the choice of embedding vectors, we look into 5 different embedding schemes, which are SBERT, doc2vec, OR2vec, USE, and TF-IDF. For 4G and 5G, we sample few data, and we see that TF-IDF performs the better because we are interested in filtering out the data that has the most similarity, and TF-IDF gives the higher sparsity on the high similarity regions. So let's talk a little bit about the TF-IDF embeddings. So TF actually measures the importance of the tokens or the terms, and IDF measures the document importance. So in general, TF-IDF measures the term importance on the document based on the whole corpus. And from these TF-IDF embeddings, we calculate the similarity based on causal similarity matrix. And here are the matrices for the 4G and 5G documents. If we consider the x-axis is the list of sequences, and y-axis is also the list of sequences, so we measure the pairs similarity. And if we look at the matrices, we see that there are brighter points. The number of brighter points are very low than the overall matrix. So if we filter the data in this way, we come out with only a few set of data points, which are very efficient to deal with. And as I talked about the uninformed fine-tuning just a few seconds ago, we try to solve the NLI task here. So NLI is like the natural language inference task. We use a very general data set here, the Stanford Natural Language Inference data set, where there are 3 levels only. We have contradiction, entailment, and neutral. But here comes the next challenge. These are not ground truths for our cellular network data, right? These are like general purpose NLP datasets. So how can we build a dataset that has some kind of ground truth for our cellular networks? For that, we devise a new kind of annotation where we, if we have two text sequences, T1 and T2, we first see if T1 is consistent with T2, if it is not consistent, if it is not related at all, or they are in the temporal ordering where T1 happens before T2 and vice versa. Also, if T1 has more information about than T2 in the same context and the vice versa. So out of these 7 annotations we devise, we map them to the general purpose NLI labeling, which gives us an idea of how to map the cellular network datasets for the NLI task. Now, using that idea, we also apply an ensemble of the language models we use. Here we use K models. K is generally 3 here. And also we use an active learning approach where an expert validates the predictions at each of the steps, and we do K steps of informed fine-tuning here. So for the ensemble, we use majority voting over the language models here. Now comes the question, if we can devise this overall methodology and find out the inconsistencies, how can we use them for the further evaluation on real-world devices or open source implementations? So for that, we take the inconsistent pair of sequences and map them to open source implementations. And later, we also devise some attack scenarios for the real-world devices. So this is our overall approach. And let's look at some of the model performances. So the candidate models here are BART, Roberta, and ExcelNet, and we also have the ENCEL. At phase 0, where we do not have any kind of information about the cellular network datasets, we have a performance of generally about 60% on top. And after 3 phases of training, we see that the best performance is always from the ENCEL or similar performance, and also the performance increase is about 25%. Now, let's look at the breakdown of inconsistencies on different categories for 4G and 5G. We found about 7 categories for 4G and also 11 categories for 5G. And in total, we have about 157 total inconsistencies. And let's look at some of the findings in more detail. So this is the example I showed on the first slide. And we found that in an open source implementation, which is very popular, SRF-STRAN, there is a code block where there are both of the substrate are used in the transition. So the first if block is actually executed by the second if block. So that's why it is clear that the developer might be confused on implementations if these are the 2 text sequences from the specifications. And this can cause also interoperability issues. And we also found different scenarios where the integrity and ciphering the descriptions are more detailed than the other. And also for another case where NCC, which is a next of chaining counter, one says it should be fresh and new, and another says it can be different, and that should be enough. And there are many other scenarios where different identifiers like GUTI deletion is suggested, but the other one doesn't suggest anything like that. So if we have some kind of findings like this, how can we look into the attack scenarios or real-world implementations? So let's take a look at that. So let's say we have this kind of scenario, as we just seen, where one suggests deletion of the identifiers, different identifiers, and another suggests just the deletion of the list of P elements. So we take the most specific one, which is the first one, and then we see if, then we ask the question if GUTI is properly deleted. So to check that, we first set up our overall test bed where we connect the devices and establish the security context. And later, after establishing the security context, we just send a reject message with the same cause, which is 13 and roaming not allowed for the tracking area. And after that, we check if the GUTI is still there, the previous GUTI is still there. So we inspect the packet, and if the GUTI is there, then we know it is not properly deleted. So this is our overall result for the device testing. We tested 17 devices from different vendors, and One column actually represents our one testing scenario, where you can see if the device implementations are consistent according to the specifications, the columns would have the same markers, either tick or cross. But we can see that many of the columns have different markings, and by orange, we try to represent a less secure scenario. And for example, like the first column where the plain text authentication request message is accepted or not, we check that after the security context has been established. So, and we see Google Pixel 7a, which is a very new device, still accept the plain text authentication message and also plain text identity request message. So in short, we define a context-aware novel framework which can identify inconsistencies from the cellular network specifications, and we take 4G and 5G specifications here, and we found about 157 inconsistent pairs out of overall 19.2 million possible pairs, and we categorize them in 4 different scenarios under the 2 cellular networks, 4G and 5G, with 7 and 11 inconsistent categories. And thank you, and CellularLint is completely open sourced. We have also evaluated the artifacts, so if you have any questions, I'm happy to take them.